So we already discussed all of the sources or cause of prestress loss that happens for the case of pretension members. So for the pretension members, the prestress losses that occur are just the prestress loss due to elastic shortening, due to still relaxation, due to creep, and lastly, due to shrinkage. So, in addition to that, for the case of post-tension members, there is actually two additional source or cause of pre-stress loss that we will study. And first on the first on those two is the loss due to friction or simply the friction loss, which usually designated as F. So, why does friction loss occur in the post-tension members? So if you can recall what I have uh, mentioned on the previous discussions, friction loss usually occurs in post-tension members due to friction between the tendons and the surrounding concrete ducts. And actually, this is mainly because of what we call the curvature. So when there is curvature, there's there will be most probably a friction that will happen between the tendons and the surrounding concrete ducts. So just to refresh you on when friction losses occur on a post-tension members. So let's say we have here a post-tension member uh, with an eccentricity equal to E. So again, if you can recall how post-tensioning is done, steel reinforcements must be placed first along with the duct, which along with the duct wherein the pre-stressing reinforcement will be inserted later on when the concrete that will be poured like this already attained its or already attained enough strength for the pre-stressing operations. So when the concrete already attained enough strength, the pre-stressing reinforcement will be inserted to the dock, and then a hydraulic jack will be placed on the pre-stressing reinforcement, which will tend to pull it, thereby applying a jacking force to it. So on that particular scenario, or on that particular stage of pre-stressing, the jacking stage, wherein the pre-stressing reinforcement tends to elongate because of the jacking force that is being applied by the hydraulic jack. The tendency is there will be friction that will develop between the pre-stressing reinforcement and the surrounding concrete ducts. And because of that friction that occurs between them, which is actually a which actually has a negative effect on the jacking force itself because it tends to minimize or reduce the magnitude of the jacking force, that that friction that occurs between the pre-stressing reinforcement and the surrounding concrete ducts tends to reduce the magnitude of jacking force uh, at this particular stage of pre-stressing. So the magnitude of that loss due to the friction is actually a function of the tendon form or alignment, like what I've said before, which is called the curvature effect. So, because if you can remember, the profile of the tendons usually used for post-tensioning members usually have variable eccentricity all throughout the length of the beam or the span of the concrete element. Unlike this illustrated here, which has a constant eccentricity all throughout the length of the beam, for the case of post-tension members, we usually use a tendon profile with variable eccentricity, like the harp tendon or drape tendon or the parabolic tendon. So because of the curvature, uh, uh, because of that intended curvature coming from the profile of the tendon, there is actually what we call friction loss due to the curvature effect. which comes from the intended curvature of the pre-stressing reinforcement. And in addition to that, there is what we call local deviations in the alignment, which is actually the accidental or unavoidable curvature, which actually adds additional friction loss to the pre-stressing reinforcement. And that effect, due to that local deviations in the alignment or the accidental or unavoidable curvature, is actually what we call the wobble effect. So if you can imagine, sometimes we cannot perfectly place the pre-stressing reinforcement. We can have local deviations in the alignment along the pre-stressing reinforcement. And because of that local deviation, which is actually not intended, therefore accidental or unavoidable, we have we friction loss occurs because of that scenario, because of that local deviation in the alignment. And again, that scenario is what we call the wobble effect, which adds up to the friction loss that is being induced from the curvature effect. So therefore, friction loss is a total of curvature effect and wobble effect. So later on, we will derive formulas for finding the curvature effect and wobble effect. So again, uh, the the frictional loss, varies linearly along the span or along the beam span or along the span of the concrete element, with the maximum frictional stress loss at the far end of the beam if jacking is from one end. So the frictional loss is actually varying linearly along the span of the beam, with a maximum value acting on the jacking end. I mean, with the maximum value acting at the far end from the jacking end, if jacking is done from one end. So you can expect that along this span of the beam, the maximum frictional stress loss will be happening at the far end of the beam. So at this particular end, if jacking is done on one end only. So after the jacking operations, wherein the pre-stressing reinforcement already experience losses due to the friction happening between itself and the surrounding concrete blocks. Therefore, the pre-stress or the pre-stressing force that will be transferred to the concrete element, which will make it bend upward, making it a simply supported beam, and forces it to support its own weight. That magnitude of the pre-stress force that will be transferred to the concrete element will obviously have a reduced magnitude compared to the jacking force, due to the existence of what we call friction. Due to the existence of what we call friction losses, which is again the loss of pre-stress acting on the pre-stressing reinforcement due to the friction happening between the reinforcement or the pre-stressing reinforcement itself and the surrounding concrete blocks. So, as the tendon is pulled with a jacking force Pj at the jacking end, it will encounter friction with the surrounding duct or sheet, such that the stress in the tendon will vary from the jacking plane to a distance L along the span of the element as shown. So if this is the post-tension members that we are post-tensioning, if you will apply a jacking force at the jacking end, so for example here, and if we will try to look at the corresponding force acting at this particular end, let us just call the force acting at this particular end as equal to Pj prime. If we will investigate the variation of the jacking force being experienced by the tendon profile starting from this jacking end to the anchorage end here, we can see that the magnitude of the jacking stress or jacking force varies along the length of the beam. So if you can see here on the graph, uh, if the x-axis here is the distance along the tendon starting from this jacking end, and if the y-axis is the tendon jacking stress, you can see here before anchorage, before the tendon is cut, the variation of jacking stress looks like this. So you can see here that it varies uh, it varies along the length of the beam. It diminishes the magnitude of the jacking stress starting from this jacking end, diminishes in value as you go away from the jacking end before anchorage. But after anchorage, after the pre-stress force is transferred to the concrete element, after the pre-stressing reinforcement is cut, you can see here that there is a sudden decrease in the jacking stress acting at the jacking end, which is this graph. The anchorage are the graph after anchorage. You can see here that there is a sudden decrease in the magnitude of the jacking stress acting on the jacking end, but it will eventually uh, uh, redeem its magnitude at a certain distance L from the jacking end. And then it will again go back to its original variation of stress, just like before the, just like on the case of the anchorage before. I mean, just like in the case of the jacking stress before anchorage, before the pre-stressing force or the pre-stressing reinforcement is cut and the pre-stressing force is transferred to the concrete element. So again, the jacking stress varies along the length of the beam. That is what we want to show here on this particular graph. It varies. Therefore, the jacking stress or the jacking force is not actually constant all throughout the length of a tendon profile like this. For the case of post-tension beams, it varies. It diminishes in value actually. It diminishes in value. So why is that? Because the frictional losses acting on the tendon profile increases along the span of the beam with the maximum value at the anchorage end. Just like what I have said. Just like what I have said a while ago. So because of that, because of the increasing pre-stress loss along the length of the span, the jacking stress along the span decreases. So they have inverse proportionality. They have inverse relationship. When the frictional force increases, therefore the jacking stress or the jacking force acting on the pre-stressing reinforcement decreases. So they have opposite effect on the pre-stressing reinforcement. So now just to derive the formula for the curvature effect. So now at this particular point, if you are not fan of derivations of formula, you can actually skip this because this is just actually the derivation of formulas for finding the frictional loss acting on the pre-stressing reinforcement. So to demonstrate how we can derive the formula for accounting the curvature effect, which is the intended curvature on the pre-stressing reinforcement, we can use this differential length of the pre-stressing reinforcement. So just imagine that this is just a very small length. So we just zoom it out just for us to be able to see it, because if we will make it a very small length, we cannot actually see it anymore. So just imagine this is just a very small length of the pre-stressing reinforcement here with a uh, which is just a uh, an arc of a circle with a center somewhere here. So just imagine that this differential length here is just an arc of a circular or it's just an arc of a circle with a center here located here somewhere here. So let us just say that this other end is at a distance x from the jacking end. So the first point on the differential length acts on the jacking end, and the other end is at a distance x from the jacking end. So for clarity of demonstration, we will just isolate this differential length here on this space here. And then again, for clarity of demonstration, we will just change the orientation of this differential length from this orientation to this orientation, just for clarity of demonstration. So again, this is the differential length, and this is the radius of the circle with an arc equal to this differential length. So let us just call the angle here of the circle with which has an arc equal to the differential length let's just call that angle equal to differential alpha, since we are dealing with differential lengths here, very small lengths. So therefore, we will also deal with very small angles. So let us just call this angle here as differential alpha. So if we will try to draw the free body diagram of the differential length of the tendon profile, the force acting on this end, at this particular end of the differential length, is equal to the force acting on the jacking end at this particular location. So let us just call that force P. And then let us just call the force acting on this other end equal to Px, the force at a distance x from the jacking end. So again, may I just recall, according to this graph here, we can see that the jacking force or the jacking stress is not constant actually along the length of the pre-stressing reinforcement. It actually diminishes in value. So you can expect that the magnitude of Px is less than the magnitude of P, which is the force acting on this jacking end. So another force that is acting on this differential length, other than this force and this force, is actually the friction force that occurs because of the friction happening between the pre-stressing reinforcement and the surrounding concrete duct. So let us just call that friction force, the magnitude of that friction force acting on this differential length, equal to dP. So again, very small frictional force, because we are considering a very small length, differential length. And then And then, if we will try to uh, put a line that bisects this angle, the alpha here, we will try to put a line here. We can actually form a right triangle. If you can remember the properties of right triangle that we have studied from our geometry class. If we will put a bisecting line here, we can form a right triangle, specifically a right triangle, which has a right angle located at this particular point here on the circle or the circular arc. So with just using the relationships between the angle of a right triangle, we can find this angle here, the orientation of the force P with respect to this horizontal line. So if you will try to compute for that, you can see that that angle is just equal to d alpha over 2, as well as this angle here. It also has a magnitude of d alpha over 2. And if you can recall from statics of rigid bodies, we can recall that friction force is just equal to mu times the force perpendicular to the friction force, which is actually in this case this force. So let us just call this normal force, normal to the friction force, let us just call it equal to differential normal force. Again, differential because we are talking about differential lengths or differential values here. So let us just call that dn. So mu here is the coefficient of friction, if you can remember from statics. So assuming that the magnitude of P here is just approximately equal to Px, since we can actually assume that because we are talking about differential lengths here. So if we will be talking about differential lengths here specifically, we can assume that the magnitude of the force acting here on one end is just approximately equal to the magnitude of the force acting on the other end, because they have a very small discrepancy in magnitude. So since they have very small discrepancy in magnitude, since they are very near from each other, therefore we can assume that they have a magnitude approximately equal. So with that, we can see that using the equation of equilibrium, if we will try to sum up forces along the vertical direction here, we can see that dn is just equal to the sum of the vertical component of this force and this force, which is just again approximately equal. So therefore their corresponding y components or vertical components will just be equal. So you just have to multiply it by 2 because there are two of them here. So that is our equation. But if you can recall from trigonometry, it was said here, it was said there that sine theta is approximately equal to theta if theta is very small, wherein theta is in radians. So since we are talking about very small angle here, since we are talking about very small angle here, we can assume that the sine of the angle is just approximately equal to the angle itself in radians. So we can say that the sine of this very small angle here is just equal to the angle itself. Therefore, sine d alpha over 2 is just equal to d alpha over 2. And cancelling 2, we can have a final equation equal to uh, this if we will try to substitute that corresponding normal force to this equation. So the magnitude of the differential frictional force acting on this differential length is just equal to this mu, which is assumed to be constant all throughout the length of the pre-stressing reinforcement, mu times n, which is the differential normal force here, which is equal to this, but since sine d alpha over 2 is just equal to d alpha over 2, we can multiply 2p by d alpha over 2, cancelling 2. The result will be p d alpha. So that will be our equation for accounting curvature effect, which is the frictional loss due to the intended curvature of the pre-stressing reinforcement. So for accounting the wobble effect or the length effect, which is the unintended curvature of the pre-stressing reinforcement, actually we will have similar formula as this. We just have to change corresponding symbols. So we will just change the mu here by k and the d alpha by dx, since wobble or length effect is actually dependent on change in length instead of change in angle in the case of curvature effect. So this will be the equation for wobble or length effect. This will be the frictional force due to the unintended curvature or deviations on alignment of the pre-stressing reinforcement. So if we will add up this effect and this effect, if we will add up the curvature effect and the wobble effect, if we will try to superimpose those two, the effect of those two, we can have a total effect of the frictional force equal to their sum. So we will just have to add up this curvature effect to the wobble effect. So we just superimpose those two to find their total effect on the pre-stressing reinforcement. We just add up them to find the total frictional effect acting on the pre-stressing reinforcement. So if we will try to divide the whole equation by p and then integrate with corresponding limits, with corresponding proper limits. Since we are in terms of dp here, the limits must be in terms of the p or the jacking force or jacking stress acting on the pre-stressing reinforcement from the jacking end, which is this, to the other end, which is, we just called it the magnitude px. And then, since this is in terms of alpha, the alpha, the limits must be in terms of alpha as well. Alpha from zero angle, from zero angle to a certain angle alpha. And lastly, since this is in terms of dx, dependent on the length of the pre-stressing reinforcement, the limits must be also in terms of length, starting from zero length to this certain point here with a length, horizontal projection from the jacking end equal to x. So simplifying the terms here, we can find this equation here. And if we will try to combine these two expressions here, we can have this equation. And then if we will try to raise the whole equation by e, so if we will try to raise e, I mean, yeah, right. If we will raise e with this, using this equation, we can see that the left side of the equation will just be equal to p prime g pj prime over px, and the right side of the equation will just be equal to e to the mu alpha plus kx. And then if we will try to cross multiply px to the right side of the equation, we will have this equation here. Pj prime is equal to pxe to the mu alpha plus kx. Actually, this is the relationship between the force acting on the jacking end and the force acting on the any other end. I mean, any other point along the pre-stressing reinforcement at a distance x from the jacking end. So this is actually the relationship between those forces. So if we will try to express this forces you see here in terms of the stress, corresponding stresses, we will just have to divide the forces by the cross-sectional area of the concrete, or I mean the cross-sectional area of the pre-stressing reinforcement. So we can divide them by the area of the reinforcement to have the equation in terms of stresses. And take note, which after dividing the forces here by the area of the pre-stressing reinforcement, we can express the equation in terms of the force or stress acting at distance x from the jacking end. That's why the exponent of e here became negative because we divided the whole equation by e to the mu alpha plus kx. So this is actually the relationship between the stress acting on a point x at a distance x from the jacking end and the force acting at the jacking end itself. So this is their relationship. So with that, if we will try to use the change in stress happening from this jacking end to a certain end here at a distance x from the jacking end, we can see that uh, the magnitude of the change in stress, which is actually due to the frictional or friction, uh, which is actually due to the friction happening between the pre-stressing reinforcement and the surrounding concrete duct. The change in stress acting from this jacking end to a certain end x distance from the jacking end is just equal to this. This is the difference between the stresses acting on this point and this point. So since we already found the magnitude of fpx, which is this, we can just substitute this on this equation, and then factoring out fpj prime, we can have this equation. So this is actually the equation for finding the loss of pre-stress due to friction acting on the pre-stressing reinforcement starting from the jacking end to a certain end at a distance x from the jacking end. So that is the general equation for finding the magnitude of pre-stress loss acting on the pre-stressing reinforcement. Although in some books you can see, or in some references, especially on the code from the previous codes, you can see a different formula for finding the pre-stress loss. Actually, that formula is uh, an estimation. So for me, I'm not actually a fan of estimated formulas. So we will just stick to this formula that we have derived here. This is actually somehow the exact, although we know that this is just estimated, but in comparison to the estimated formula, we can see that this is more exact than that formula, which is just estimated, which you can see on the code from the previous codes and other references. So in addition to this information that we have here, in order for us to find alpha, the angle of curvature of this differential length here, we can use the concept that we have derived from our surveying course. So if we will assume that the length of the tendon, which is the colored green here, is just approximately equal to the horizontal distance of this point to the jacking end. If we will assume that this colored green here is just approximately equal in length to this length x here, and if we will try to recall from surveying the relationship between the angles and the distances from surveying, we can see that the angle of this, so again, the central angle of this is just equal to alpha, is this angle here. So with that, since that is alpha, from surveying, we can see that this is also alpha. And again, from surveying, we can see that if that is alpha, this is alpha over 2, and this is also alpha over 2. So using the concepts from surveying, we can find a right triangle here with a right angle at this particular location. So using trigonometric functions or relations, we can see that the tangent of this angle is just equal to this distance m, which is actually called the middle ordinate. The tangent of this angle is equal to this distance m divided by this distance, which is actually equal to x over 2, if this is the whole distance x. So again, this x here is somehow related to this distance. So you can imagine that this x is just equal to this x. So again, using the triangle that we have formed here from surveying, we can see that tangent alpha over 2 is just equal to m divided by this distance, which is equal to x over 2. And if you will try to recall again from trigonometry, the tangent of theta is just approximately equal to theta if theta is very small, which is again actually the case for the uh, the angles that we are considering here, like for the case of alpha. So the alpha here is approximately very small. So therefore, its tangent will be approximately equal to the angle itself expressed in radians. And again, from surveying, try to recall that m is just equal to 2y, meaning this whole distance here just divides the distance here to this distance here into two equal parts. So if this is y, this is also y, or in equation form, m is just equal to 2y, twice the y here. So using those information, we can see that this equation can be reduced to this equation, since tangent alpha over 2 is just approximately equal to alpha over 2 according to this statement here. And then since m is just equal to 2y, if you will try to substitute all of those values here, you can find this magnitude of alpha, the angle of curvature, which is again in terms of radians. So you have to keep in mind that that angle is in radians. So you can use this formula if you have no other way to find the angle alpha, the angle of curvature, between the point on the pre-stressing reinforcement that you want to find the the change in friction force or jacking force, or the friction force, sorry, at a certain point on the or along the pre-stressing reinforcement. You can use this formula. Uh-huh. So that is how you can find the magnitude of the pre-stress loss acting on the uh, pre-stressing reinforcement due to friction between the pre-stressing reinforcement itself and the surrounding concrete ducts. So again, may I just recall, this pre-stress loss that we have derived here is a function of the distance of the point that you want to consider with respect to the jacking end. So you have to specify the distance of the particular point that you are considering along the pre-stressing reinforcement with respect to the jacking end. So if you want to find the total pre-stress loss acting on the whole pre-stressing reinforcement, therefore you can just specify the magnitude of x equal to the whole length or the whole span of the beam, since we are assuming that the length of the tendon is just approximately equal to the magnitude of x here, the distance from the jacking end. So if you want to find the total loss acting on the whole pre-stressing reinforcement, therefore the x that you have to use is the x corresponding to this particular location, the location of the anchorage end. So with that, you can find the total pre-stress loss acting on the pre-stressing reinforcement. So if you can notice on this equation that we have derived for finding the magnitude of the pre-stress loss due to friction acting on the pre-stressing reinforcement, you can notice that we have terms mu and k here, which are actually the coefficient of frictions and the coefficient for wobble effect. So you can find the values of those on the different codes that you can refer to. So if you will try to refer to ACI 318M-08, you can see the corresponding values of K as well as mu for finding the pre-stress loss due to friction for post-tension tendon, since obviously friction force or friction loss just uh, happens on post-tension tendons. So these are the corresponding K for wobble effect and corresponding mu for curvature effect that you can use to find the magnitude of the pre-stress loss due to friction. So you can find it on ACI 318M-08. So if you will try to look on the ACI 318M-11 and -14, you can no longer see this table, and I don't know why is that, why I don't know why they remove this table on the code itself. But if you will refer on the previous versions of ACI 318, specifically the 2008 version, you can still see this particular table here. Or if you will refer to the PCI, Prestress Concrete Institute, you can see a somehow similar table. So you can see here that the coefficients K and mu are dependent on the type of tendon. So if there are so the different types of tendons are specified here, and their corresponding K and mu, the coefficients for wobble and curvature effect respectively. So you can use this values you see here on these tables.